stability. Why is stability in a system very important? And what happens if the system goes unstable? What happens if we give an input to the system and the output is unbounded and it increases exponentially? And how to check whether the system is stable or not? Is there any criterion or any step of guidelines that we can follow to check the stability of the system? And in such case, what is that stability criterion and how to check the system is stable or not? So that will be today's discussion. One thing I would like to say that you have been very interactive, and this session was so nice, like one of my best sessions in the recent times. And you have also joined by going through the lecture site, so it helps you as well as me, so that it will motivate me to teach more and more, and also you'll also get benefited. And thank you for making this
Thank you, sir,
session
for
very
the
interactive. Welcome back, everyone. We are in the week 4 problem solving session of the NPTEL course Control Engineering, and week 4 is about Introduction to Stability and Routh Hurwitz Stability Criteria. I am Teja Golla, a 5th year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. I hope you can see my screen. So today's point of discussion will be stability. First, we'll discuss about stability, and then we'll discuss about Routh Hurwitz criteria, and then we'll also discuss about one important concept called sensitivity. So starting with stability. So why is stability important, and how do you say a system is stable or unstable? So let us consider one example to understand what is stable, what is unstable, and what is marginally stable. So to start with, I'll consider one simple example, the known one, the simple pendulum. So let us consider, I'm sorry. So let us consider a simple pendulum. And I'll consider 3 scenarios. So in the first case, so I have a string and then I have a ball. So imagine I have taken the ball here. And then I have left the ball at that position. Now, as you know, the ball will keep on oscillating to and fro, and then it will finally settle here, assuming there is resistance. If we consider the air resistance, if we consider the friction, then slowly it will come to the original position and it will rest here, considering the resistance, considering the air drag. So in the presence of air drag. So in this case, once it rests, even if you give perturbation, even if you give some certain perturbation, it will come back to its original position. So no matter how much is the disturbance, it will come back to its original position after certain time. So this system is called stable system, which will return to its original position even under some perturbance or some disturbance. So this system is called stable system. Hemalata, can you hear me?
Good evening, sir. Yes, sir.
Okay. Yeah. My screen is also visible, right?
Yeah, right. Yes.
Okay. So just I'll quickly explain what I've been telling. So first, today's topic of discussion is stability. So I have considered one simple pendulum example. So I have one string with a length L and I have a ball connected to it, bob. And then if I give certain perturbation when it is at steady state, it will move to and fro, and in the presence of air drag, it will eventually settle down at its original position, which is the initial position. So this is called stable system because if we give any disturbance or any perturbation, the system will eventually come back to its original position after certain time. Now I am considering another such example, the same simple pendulum, but I will not consider the air drag. Say there is no air drag, which means there is no friction. So if I give any perturbation, so if I give any force, it will keep on oscillating, right? It will not come back to its original position, which is this. So it will keep on oscillating. And then because there is no air drag, it will keep on oscillating. So depending upon the perturbation, the oscillations distance can increase. If I give more force, then it will oscillate more. If I give less force, then it will just oscillate around that point. So in this case, the system is not neither unstable nor stable, because it is neither coming towards the initial point nor it is going away from the initial point. It is in fact oscillating around the operating point. So these systems are called marginally stable, because it is just oscillating and the oscillations are fixed depending upon the perturbation. The oscillation amplitude is fixed, but once the input is given, the oscillations are neither growing nor decaying. So if the oscillations keep on growing, then it is unstable system. If the oscillations keep on decaying, then it is stable system. If they remain the same throughout the rest of the operation, then it is marginally stable system. Now I'll consider another case, but instead I'll consider this is my initial position, and say if I give some perturbation, what happens? So this is consider this is not a thread. Consider this as a stick, because for thread this is not applicable. Consider this is a stick, a wooden stick connected to a ball at the end. So this is a ball. So now if I give any perturbation, then what happens? It will keep on oscillating, right? So it will keep on oscillating like this, like this, like this. And in the presence of air drag, what happens? It will finally settle at the this position. So finally it will come this position in the presence of air drag. So the oscillations will die out, but it is not coming to the initial position. It is in fact going to some other position, and it will never go back to the initial position if there is some perturbation, because the initial position is an unstable position. So under any presence of some disturbance, it can be air or if we push using our finger, it will never come back to its initial position, and such systems are called unstable systems. So is this clear till this point?
Yes, sir.
Okay. So now this is just an introduction to understanding what is a stable, what is unstable system. But to define it mathematically, so there is something called Bibo stability. So we have Bibo stability, which means bounded input, bounded output stability. So as the name says, if the input is bounded and if the output is also bounded, then the system is stable. But if the input is bounded and the output goes unbounded, then it is not Bibo stable. Bounded input, bounded output. So again, this is in time domain. So we'll be discussing both time domain as well as frequency domain. But as I have mentioned in the earlier classes, frequency domain will be more easy to understand regarding the stability, because S domain will make our life simpler. Eventually we'll go to S domain, but we'll start with the time domain. So let me quickly draw one system. We have a system. We have one system, and say it is H of t, and we have U of t and Y of t. So if the input is bounded, output should be bounded if the system is Bibo stable. If it is not, then it is not Bibo stable. So in this case, the condition is the impulse response is absolutely should be absolutely integrable. The impulse response should be absolutely integrable. Okay, so under this condition, we can say the system is Bibo stable. Absolutely integrable means impulse response, we know it is h of t. So absolutely means mod of h of t dt from minus infinite to infinite. This value should be finite and it should not go to infinite, which means the integration should have a finite value. So under this condition, we can say the system is Bibo stable. So this is in time domain where we are giving a bounded input, and then we'll check whether the output is bounded or not. So under these circumstances, we can say that the input is bounded, so the output should be bounded if the system is stable, else it will keep on growing and the output is unbounded. So we can say that the system is not Bibo stable. So is this concept also clear?
Yes, sir.
Okay. Now we'll go to frequency domain, because now we have discussed with time domain. Now let us go to frequency domain and see what does stability say in the frequency domain. So I'll start considering a first order system. So let us consider a system G of S. The transfer function is say A by S plus A. So now if we consider G of T, say if I consider G of T, so what will be the inverse Laplace of this?
E to the power minus 80.
Yes, very good. A into e to the power minus 80. So this is the inverse of the inverse Laplace of this G of S. But if you see, my Bibo stability says that this is the impulse response, right? Basically, G of S is the transfer function of the system. So G of S is nothing but the transfer function of the system. So if I consider G of T, which is H of T in this case, so the impulse response should be absolutely integrable. So if I consider this, and if I have to consider that whether this is absolutely integrable or not, let us consider the expression. So integral minus infinite to infinite a into e to the power minus 80 dt. So if I consider this, I'll get a by minus a into e to the power minus 80 minus infinity to infinity. Okay.
Sir.
Right. So
Yes,
if I consider here, I can consider two cases. And I think we should consider from 0 to t, because our system starts from t equals to 0. So we'll not consider minus infinity. So just, it is my bad. We'll consider from 0. Sorry. Because we are considering from 0, our Laplace transform also starts from 0, because we are considering the system starts from t equals to 0. So this is my bad. So the integration starts from 0 to infinite. So if you consider a greater than 0, and then a less than 0, in the first case, what will be the integration output?
A greater than 0. A e to the power minus 80. Sir, 0 to infinity. T is 0. A e to the power minus a.
If you put t equals to 0, it will be e to the power 0, 1, right? So a by a, right? A by a. Whereas in the case of a less than 0, a is negative. So e to the power e to the power some positive number into infinite, then it will tend to minus infinite. So this is unbounded. In this case, it is unbounded. So we can say that this is stable. Left side, it is stable because it is bounded. Whereas this condition, it is unstable. So we got a condition that system is stable if a is greater than 0. Now if we check the pole location, let us check the pole location. So pole location is s equals to minus a, right? So a is positive means s is now negative, right?
Yes.
Yes. So as long as s is having a negative, now here we have considered real part only. Even if it is complex, if the S is consisting of negative real part, then the system is stable. If it has positive real part, then the system is unstable. So if we consider the axis, so if we consider this axis, so S has two parts. One is sigma and the other one is j omega. So S is equals to sigma plus j omega, right? So if we consider sigma is the real part of S, or sigma, and then here imaginary part of S, or j omega. So we can say this region, left side region is stable, whereas this right side region, so let me change the color, this right side region is unstable. So we will get this left side region is stable, and then the right side region is unstable. What about the poles if they lie on the imaginary axis? So if they lie on the imaginary axis, then they are called marginally stable. So this is marginally stable. So if we have poles on the imaginary axis, so just one more point. So this is also important point. So if we have poles on imaginary axis, then it means it is marginally stable, because the poles on the imaginary axis will result in oscillations. Say we have s equals to plus or minus j3, which means 1 by s square plus 9. So 1 by s square plus 9 corresponds to a sine term, right? So we will get sinusoid oscillations. But if you consider repeated roots on the imaginary axis, say I have s equals to plus 3j plus 3j minus 3j minus 3j, which means I have four roots, but two of them are overlapping and all of them are on the imaginary axis. Then it will have 1 by s square plus 9 whole square. So now if I do the inverse Laplace transform, I will get t into sine omega t. So now this t term will make sure the oscillations will keep on increasing. So if there are repeated poles on the imaginary axis, again it is unstable. So if we have repeated poles, repeated poles on imaginary axis, means the system is unstable, because we'll get an additional t term, and this t term will increase with time. So the oscillations that are caused by the poles on the imaginary axis will keep on increasing because of these repeated poles. Because in the denominator we have 1 by s square plus 9 whole square. So if you consider the inverse Laplace, we'll get t term in the time domain. So we'll get t into sine omega t. Sine omega t is oscillations. T into sine omega t is an oscillation that is increasing with time unboundedly. So we cannot get the absolute integration for that, and that's why it is also unstable. So is this concept clear till this point?
Yes, sir. Yes, sir.
Okay. So now we can understand if we are going into S domain and if we are checking the stability of the system, the objective is to find the pole location. So if it's a first order or second order, we can find the pole location. But say if the order has increased to sixth order or fifth order, how do we know the pole location? We don't have to calculate whether the pole is at -5 or -10, but we just have to ensure that pole is not on the RHP side. So we have to check whether the pole is on the left side, LHP or RHP. So again, this region, red color region, is called RHP, right half plane. So this, if this is a plane, then it is on the right side. Similarly, if this is a plane, it is on the LHP. So we have imaginary axis separating the plane into two regions. On the right side, we have RHP, right half of the plane. On the left side, we have LHP, which is the left hand side of the plane. So now the objective is to find whether there are any poles on the right side or not. If there are no poles on the right side, then system can be stable or marginally stable. But if the poles are only on the LHP and not even on the imaginary axis, then it is stable. But say there are few poles on the imaginary axis, then it is marginally stable. But if there are repeated poles on the imaginary axis, then the system is unstable. So now Routh Hurwitz criterion is criterion using which we can identify the pole location, whether they are in the LHP or whether they are in the RHP. So the criterion objective is to find the location of the poles of the higher order polynomial. Because for lower order, it is simple. Only the difficulty comes when the polynomial order increases. So if you see, we are only bothered about the poles of the g of s. So we are only bothered about the denominator of the g of s and not the numerator. So the denominator is called characteristic polynomial. So if you have a system, I'm not going too fast, right? Is the pace okay?
Yes, sir.
Okay. So once we, I hope you have gone through the lectures, right?
Yes, sir.
Okay, yeah. So this is u of s and then y of s. So now y of s is equals to y of s by u of s is equals to g of s by 1 plus g of s h of s. So if I call this numerator polynomial n of s by denominator polynomial, so this denominator polynomial it corresponds to the poles of the system. And now the objective is to use Routh Hurwitz criterion to find the poles of the system. So this denominator polynomial is of our interest, and this is also called as characteristic equation, which decides the stability of the system. So in the future also, we'll find different ways of finding the stability. So Routh-Hurwitz criterion is one of the criterion where you will find the poles. But in the future, we'll also see different type of different ways. One is by root locus method. Another one is by Bode plot method. Another one is by Nyquist theorem. So using this Nyquist plot also, we'll see how to check the stability of the system. But we'll start with the Routh-Hurwitz criterion. And all are S domain, as uh, we have specified that S domain is what we will be diving into more compared to the time domain. So now the denominator, this characteristic equation, will apply Routh-Hurwitz criterion and check the pole location. So Routh-Hurwitz criterion has two conditions. One is necessary condition and another one is sufficient condition. So what is necessary condition? Necessary condition means if any polynomial fails to meet that necessary condition, we can say that there are poles on the RHP side. But if it meets that necessary condition, is it sufficient to say that poles are on the left hand side? No, it is only necessary condition, which means it has to satisfy so that we can say that now we have to check whether the poles are on the LHP or RHP. But if it doesn't meet the necessary condition, we can for sure say that the poles are on the RHP, some of the poles. So what is this necessary condition? So first point is the polynomial should have all coefficients. The polynomial should have all the coefficients, which means say I have s cube plus 1s square plus 2s plus 3. If the polynomial has all the coefficients, then one of the necessary condition is met. But for example, I have considered s square plus 5s plus 3 equals to 0. S S cube plus 5s plus 3 equals to 0. So s square coefficient is missing. Then I can say that one of the coefficient is missing. So it fails to meet the necessary condition. So some poles are on the RHP side. This is one necessary condition. The second condition is the coefficients of all the coefficients of all the, or I should say all the coefficients should be positive. All the coefficients all the coefficients should be positive. So I'll give you three examples. You let me know whether the necessary condition is met or not. So let us consider one example. First example is s square plus 5s plus 9 equals to 0. Is the condition met, necessary condition?
Yes, sir.
Yes. So I'll
Both.
consider s cube minus 5s square plus 2s minus 3 is equals to 0. Is the necessary condition met?
Yes, sir.
Which
Minus
condition is not met?
second, all the coefficients should be positive.
Positive.
Yes, sir. -5 and -3.
Yes, very good. So now I'll consider another s power 4 plus 2s square plus 3s plus 4 is equals to 0. In this case,
So the cube term is not there, sir.
yes, very good. So one term is missing, which means all the coefficients are like all the, sorry, the polynomial should have all the coefficients, like should have all the degrees, or all the coefficients should be 5, which means it is non-zero. Yeah, so the polynomial should have all the coefficients and all the coefficients should be positive. So only in that case we can say that the necessary condition is met. Now we will apply Routh Hurwitz criterion. If the necessary condition has not been met, then we can straight away say that the necessary condition has not been met. So there are few poles on the RHP side. So we can straight away say that the system is not stable. Okay. So now coming to Routh Hurwitz criterion. So I'll just give one generic example, then we'll solve more problems. So we'll consider the characteristic polynomial Q of S. Say an into s to the power n plus an minus 1 into s to the power n minus 1 plus an minus 2 into s to the power n minus 2 plus up to so on plus a2 into s square, because all the coefficients should be there and all are positive. So I am considering all are positive, all the coefficients should be there. So now we have to draw the Routh table. So how do we draw? So on the left hand side, we have all the coefficients. So we have s to the power n, then s to the power n minus 1, then s to the power n minus 2, up to so on we'll have s to the power 1, s to the power 0. So all the power should be there. So in the first two rows, first two rows will be coming from the polynomial. So the first row will start with s to the power n coefficient. So we can say that it is an. Then we'll skip the next polynomial and we'll go to an minus 2. So an minus 2, an minus 4 up to so on. And s to the power n minus 1 starts with an minus 1. Then we'll skip the next one, an minus 3, an minus 5 up to so on. So from s to the power n minus 2, now we have to calculate the coefficients and then we'll be entering the values. Okay. So here say it is bn, say bn minus 2, bn minus 3. So bn is calculated by using these four terms, and how it is calculated, bn is an minus 1 into an minus 2 minus an into an minus 3 by an minus 1. So this element is calculated by multiplying these two minus product of these two divided by an minus 1. Similarly, bn minus 2 will be calculated using these four terms. Okay, so we'll get bn minus 1, sorry, bn minus 2 is equals to an minus 1 into an minus 4 minus an into an minus 5 by an minus 1. So in that way, we'll calculate bn minus 2. Similarly, if we are calculating this element, say here, whatever element will be there, in order to calculate that, we'll use these numbers. And whatever we have to calculate this one, we'll use these four elements. So in this way, we'll finish the Routh table. And then we are interested about the first row. So all the elements in the first row should be positive. Then in that case, we can say all the poles on the LHP side. So the number of sign changes, say it has changed from positive to negative and negative to positive. Then there are two sign changes. So number of sign changes in the first column, number of sign changes in the first column is equals to number of poles in the RHP. So if there are no sign changes, then there are no poles in the RHP 0. But what if it becomes 0? what if the entire row becomes 0? So these are some border cases that we'll consider in the problems that I have considered in the upcoming slides. There I'll mention how to deal with such corner cases. So is that clear till this point?
Yes, sir.
Okay. So now let us consider one polynomial. So to start with, I have considered third order polynomial. So we'll first write the Routh table. So we'll have s cube, s square, s to the power 1, s to the power 0. So in the first row, what will be the elements?
1, 11.
1 and 11, because we'll have s cube coefficient and s coefficient. And in the second row,
6.
6 and then 6, right?
Sir.
So now calculating the s to the power 1 coefficient, what I will be doing is I'll be first multiplying this and then minus this into this by 6, right? So 6 into 11 minus 6 into 1 by 6. So what is the value?
10.
10. So this value is 10. And then this value, there is nothing because there are no elements on the right hand side to calculate that. So now cross means we can consider it to be 0 as well because there is no element. So we can consider it to be the 0. So now in order to calculate s to the power 0, what we will do, we will be considering 10 into 6 minus 0 into 6 by 10. So what will be the value? 6, right? Okay. So now we'll consider this first row. So we'll consider this, sorry, first column. Are there any sign changes? All
No,
are
sir.
positive. So there are no sign changes. So we can say no sign changes. So there are no sign changes means no poles in the right half plane. So the system is stable. Clear?
Sir.
Both of you?
Yes, sir.
Okay. So now let us solve one more problem. So here now I have considered a little bit higher degree. So previously it was s to the power 3. So if you see, we got here 2, 2 and then one element in the each row. So it is relatively easier. Now let us start with s to the power 5 because this is fifth order. Again, we have directly calculated Routh Hurwitz criteria, but I forgot to ask one question. Does this polynomial meet the necessary condition?
Yes, sir.
Yes, so it meets the necessary conditions. So then only Routh Hurwitz criteria makes sense. Else, it doesn't meet the necessary conditions. So Routh Hurwitz criteria also says the same thing. So no need to even go to RH criteria. We can directly strike it off saying the system is unstable. Similarly, does this meet the necessary conditions?
Yes.
Yes, sir.
Yes. So now we can start the Routh Hurwitz criteria. I hope you are also solving along with me so that.
Yes, sir.
Yeah, go. So s to the power 5, s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. So first row, what are the elements?
5, 1, 1, 1, 3.
1, 1, 3. Very good. And the second row?
2, 2, 4.
2, 2, 4. So now s cube first element will be what? 2 into 1 minus 2 into 1 by 2, right?
Yes, sir.
So it is 0.
0.
Now the next element, how to calculate? 2 into 3 minus 4 into 1 by 2. So how much is that?
1.
1. Very good. So I have calculated till this row, but now from this row I cannot calculate because 0 into 2 minus 1 into 2 by 0 is infinite. So I do not know how can I proceed further. So here comes the first condition. First, special case. So what is the special case? So I'm putting it star. If the first element in any row becomes 0, then replace it with epsilon, which is a positive number. It can be negative, but let us start with positive number because we are considering the sign changes. If you consider negative, it will be confusing. So we'll replace it with a positive number epsilon, just slightly more than zero, small value which is higher than zero. Then replace with epsilon greater than zero and finish the Routh Hurwitz table. So we'll consider it to be some small positive number and then we'll finish the table. And then we'll see if there is any row where the first element is becoming negative or not. So we'll replace it with epsilon. So now what I will do, I'll remove this and then I'll replace it with epsilon, which is very small value higher than zero and it is positive. So now using epsilon, now let us finish it. So this row, the last element is cross because there is no other element that we can calculate. Now S square first element will be what? Anyone? Anyone?
Four epsilon.
These right? We have to multiply with this, right?
2 epsilon minus 2 by epsilon.
Okay, 2 epsilon minus 2 by epsilon. So what is this? 2 minus 2 by epsilon, right?
Yes, sir.
2 minus 2 by epsilon. So this is 2 minus 2 by epsilon. And then cross we can consider 0. So let us consider 0 only. And now the next element will be epsilon into 4 by 0 into 2 by epsilon. So what is this? 4, right? 4 epsilon minus 0 by epsilon. 4. Both of you are getting it, right? It is 4 because one element is 0 means this element will come down.
Yes, sir.
Okay. So now let us calculate s to the power 1. So I'll make more space here. So s to the power 1 and s to the power 0. So s to the power 1, what will be the value? So now this into this minus this into this by 2 minus 2 by epsilon. So if I calculate on the side, I'll get 2 minus 2 by epsilon minus 4 epsilon by 2 minus 2 by epsilon. So we can consider now if I calculate, it will be 2 epsilon minus 2 minus 4 epsilon square by 2 epsilon minus 2, right?
Yes, sir.
Okay. So if you calculate this, we are getting minus 4 epsilon square plus 2 epsilon minus 2 by 2 epsilon minus 2, right? So this will be minus 4 epsilon square plus 2 epsilon minus 2 by 2 epsilon minus 2. And then this element will be 0 and the last element will become 4. Agree?
Yes, sir.
Yeah. So now how to determine? We'll have to consider the first row again. So this is the row, sorry, first column, my bad. So this is the column we are interested in. So now considering this column, what can we say? So epsilon is a small number, right? So I can consider epsilon to be 0.01 and then calculate the first row and then see if there is any sign change. So is there any sign change?
Yes, sir.
Where?
S square term because 2 minus 2 by epsilon will be negative.
Yes, very good. So what I'm considering is, so I am considering epsilon to be very small. So if I consider epsilon to be say 0.01, then as you said, this will be positive. This is also positive. This is also positive, but this is negative. This will be positive because if you substitute epsilon to be 0, then it will become 1.
Yeah.
Or even maybe we have to check whether in some cases whether it is exceeding, but epsilon substituting to be 0, it is coming like -2 by -2. In some cases it can come -1.99 by -2.01, something like that. But both numerator and denominator will be negative, so it will be close to 1 but positive, maybe 0.9 or 1.01. But it is positive. This is also positive. So how many sign changes are there? Here one negative and negative to positive. So two sign changes are there, right?
Yes, sir.
So we can say that two sign changes, which means how many poles in the RHP?
2.
Two poles in the right half plane. So the system is stable or unstable?
Unstable, sir.
Unstable. So this is one border case that we have considered where the first element will become 0. And then how to do that? We'll replace it with an epsilon greater than 0, and then we'll finish the Routh table. Then we can choose epsilon to be a small positive number, which is say 0.01 or 10 to the power -3, whatever. And then we'll see whether there are any sign changes or not. Sometimes it will be very clear, sometimes it may not be. So in that case, you have to substitute epsilon and see whether any number is becoming negative or not. In such cases, if there is any sign change, then the system is unstable. Is this problem clear for both of you?
Yes, sir.
Okay. So now can we move to the other problem?
Yes, sir.
Okay. So here also we have considered, I hope 1, 2, 3, 2, 1, 1. I hope both are not same. 1, 2, 3, 2, 1, 1. Yeah, both are not same. So let us solve this problem again. So we'll start from s to the power 5 and then s to the power 4, s to the power 3, s to the power 2, s to the power 1, then s to the power 0. So what will be the elements in the first row?
1, 3, 1.
1, 3, 1. Very good. In the second row?
2, 2, 1.
2, 2, 1. Very good. So now if you multiply this 2 into 3 minus 2 by 2. So what is the first element?
2.
2. What will be the second element?
Minus 1 by 2.
2 minus 1 by 2, right?
No. Oh, this 1. 1 by 2.
1 by 2. So 0.5. So second element is 0.5. There is less than a minute. So if this meeting ends, kindly join back so we can continue with the problems. So now coming to s square. So now what will be the value? So I'll use a different color. So 2 into 2 minus 2 into half by 2. So what is this value?
3 by 2.
3 by 2. So 1.5. And then this element I can consider 0. So 2 into 1 minus 0 into 2 by 2. So it will be 1, right?
Yes, sir.
Yeah. So now if I have to consider, then I think this meeting might end. If this end, kindly join back. So now what will be the value? 1.5 into 0.5 minus 2 by 1.5. So if you have calculator, you calculate it and let me know.
Yes, sir.
So it will be 3 by 4, right? 0.75 minus 2 by 1.5. So how much is it coming?
0.8.
Sorry, your voice is low, whoever is saying.
Minus 0.833.
Minus 0.833, okay. So if we are doing that, we'll get minus 0.833. This is 0, so this also will be 0. And what will be the last element?
0.
This element, s to the power 0. We have to multiply these two, right? This into this, minus this into this by minus 0.833.
1.
1. So one trick is say if we are calculating this element and then or I can start from here. So if this is 0, right, then this one will come here. Similarly, if this is 0, this one will come over here because it means basically this is 0. So basically what we are doing is we are multiplying this into this by this, right? So this element will directly come down here. So for ease, I'm putting 0. So even if you calculate, you can get it. Else, if any element has 0 below that, then this element will directly come into the next row. So this one is coming over here. The same one is coming over here. So now in this problem, how many sign changes are there?
2.
1. Okay,
1
2.
or 2?
2.
2.
2, right? So from here to here, there is one change, and from here to here, there is another change. So there are two sign changes. So how many poles and whether the system is stable or not?
2 poles and system is unstable.
Yes. So 2 poles in the RHP, system is unstable. Okay. So we'll move to another problem. Does this meet the necessary condition criteria?
Yes, sir.
It meets, right, both the conditions?
Yes, sir.
Okay. So now we'll start solving from s to the power 6, s to the power 5, s to the power 4, s to the power 3, s to the power 2, s to the power 1. Then we'll have s to the power 0. Okay. So what will be the first row?
1, 7, 14, 8.
1, 7, 14, 8. Second row?
3, 15, 12, 0.
3, 15, 12, 0. Yeah, very good. So let us start from this first row. So 3 into 7 minus 15 by 3. So what is the first element?
2, sir.
2. Yes, very good. And then next element is 3 into 14 minus 1 into 12 by 3. So how much it will be?
Yes, 10.
10, right? So this is 10. And for calculating this, as I have said, any element which has 0, it will come directly into the next one. So I can bring the 8 directly here. But if you have any confusion, you can calculate 3 into 8 minus 0 into 1 by 3. So which is 8. Clear until this row?
Yes, sir.
Yes, sir.
Okay. So now if I consider S cube, let us consider a different color, orange color to the rows. So what will be the first element? 2 into 15 minus 10 into 3 by 2?
0.
0. So we might think that because it is 0, it will come under that special case that we have solved before, and we'll replace the epsilon. We cannot take the decision until we finish the entire row. So now coming to the other element. So this one, what will be the other element? 2 into 12 minus
0, sir.
Again
0,
0.
right? Again 0. So this is different, slightly different from what condition we have faced in the previous problem. So in this problem, we have considered or we have faced only one element to be 0 in the entire row, and that is first element. If it is middle element, there is no issue as of now, but the first element has become 0. So we have to replace it by epsilon and then proceed further. But we have here entire row to be 0. So in this case, what we'll go is we'll go to the polynomial that is above. And in this case, if the entire row is becoming 0, the polynomial above that this row is called auxiliary polynomial. So this polynomial is called auxiliary polynomial. Auxiliary polynomial. And auxiliary polynomial is factor of the given polynomial. So if I find the roots of this polynomial, then those are the roots of the given polynomial. So auxiliary polynomial is a factor of the given polynomial. So these are the conditions of the auxiliary polynomial. So again, I'll write the special case, what we got. So the special case is if an entire row becomes 0, then how to get that row? So you need to differentiate the above row. Differentiate the above row, and that above row is called auxiliary polynomial. So basically in this problem, whatever auxiliary polynomial that we got is 2 into s to the power 4 plus 10 into s square plus 8, right? So the auxiliary polynomial that we got is how much? 2 into s to the power 4 plus 10 into s square plus 8 equals to 0, right?
Yes, sir.
So now if you differentiate this, whatever elements that you will be getting, that will be used in S cube. So now if we differentiate it, what we will get? 8s cube plus
20s.
20s plus 0. So if I remove this, I'll get 0. So basically what we have done is we have differentiated. Differentiate with respect to s. So we have differentiated it with respect to s to get the lower order polynomial. Now this will be used as this row, and then we'll proceed with the Routh Hurwitz criterion. So we got 8, 20, and 0, right? So let us replace 8, 8, 20, and then 0. So basically we have differentiated d by ds to get this. So now let us proceed further. So now 8 into 10 minus 2 into 20 by 8. So we have 80 minus 40 by 8. So what is the value?
5.
5. Now next value, because this is 0, I can take the above number and then directly put it 8. Got it? 8 into 8 minus 0 into 2 by 8. If you
Yes, sir.
calculate, you will also get a similar one. So 8 into this minus by 8. And then the last term is 0. So now to calculate s to the power 1, I'll do 5 into 20 minus 8 into 8 by 5. So how much is the value?
7.2.
7.2. Okay, very good. And then the last element will be 0 minus 0. So it is 0. And what is s to the power 0 value? That we'll get by 7.2 into 8. Yeah, very good. So because it is 0, I can pull down the 8. Okay, so now we are concerned about the first column. But before making any comments, I have to tell about this auxiliary polynomial. First, we have encountered one row where all the elements are 0. Then we have used the auxiliary polynomial to get the coefficients of that particular row. And then we have finished the Routh table. Okay, but now there is something that we need to learn about this auxiliary polynomial, which is auxiliary polynomial. So first of all, this polynomial is a factor of the original equation or the given polynomial. So this polynomial is a factor of the given polynomial. So we can find these roots, and then those roots will also satisfy the given polynomial. So we can directly get the roots from this auxiliary polynomial. So this polynomial is a factor of the given polynomial, and also the roots of auxiliary polynomial, the roots of the auxiliary polynomial are symmetric with respect to origin. Are symmetric with respect to origin. So again, I'll consider three cases. What are the possibilities of the roots? So I'll consider one here, and then I'll just copy so that I'll use it for the other two cases. So Control C, Control V, Control V, Control V. So if say the roots of the auxiliary polynomial are real and it has to be symmetric. So if one is positive, other one will be negative. And then one thing, so in this is the j omega plane, right? So in this S plane, basically S plane, we will be plotting the poles as well as the zeros. So when I say or use any terminology, I have to define. So the roots of this numerator are called the roots of the numerator are called zeros. So roots of this numerator are zeros, and the roots of the denominator are called poles. And usually zeros are denoted by O on the S plane, and poles are denoted by cross on the S plane, and it is universal. So in any book that you refer or any course that you refer, that is the universal notation that people follow, so that there will not be any such uh, confusion. So now we are dealing with the poles. So that's why I'm using this cross mark. So now we are not dealing with zeros because zeros will not define the stability. Only poles will define the stability. So whatever Routh Hurwitz we are doing, that is for poles. But zeros will come in the upcoming class where we consider root locus. Then we'll discuss more about zeros. So this is one case when the poles are real, then they're symmetric about the origin because it can be plus or minus 3, plus or minus 5. So one will be on the left side, one will be on the right side. So now if the poles are imaginary, say 2j, then it has to be symmetric. So it can be plus or minus 2j, plus or minus 4j. So it will be something like this. But what if it has, plus or minus a plus jb? So then it can be a plus or minus something like this. So one on that side and one on this side. And if it happens in 4, then we'll have one more here and one more here. Basically, it is symmetric about the origin. That's what we want to say. So that we can also check in any problem that you get the auxiliary polynomial. So let us check. In this case, the auxiliary polynomial is 2 into s to the power 4 plus 10s square plus 8, right? So if we equate it to 0, then let us calculate the roots. So we'll have 2 into s to the power 4 plus 5s square plus 4 equals to 0. So can we factorize this?
10, sir.
Sorry,
Be,
s square plus something like, can we factorize this? S square plus 5s square plus 4 to find the value of s. Can I write like this? S square plus 1 into s square plus 4 equals to 0.
correct, sir.
Yeah, so now what is the value of s?
Plus minus 1 and plus minus 2.
Plus minus j, right? It is imaginary.
Sorry, yeah, j.
Plus minus j plus minus 2j.
Yes, sir.
So now I calculated 4 roots, and then if I plot it on the plane, I will get plus minus j. These are one set of poles, plus minus 2j. Okay. So now I have calculated the 4 roots of the auxiliary polynomial, which also happens to be the roots of the original polynomial. So the original polynomial has 4 roots on the imaginary axis. Now what about the other 2 roots? Because it is 6th order. So now in order to know about the other 2 roots, we'll come back to the first column of the Routh table. So based on this, can you tell what about the other 2 rows? Sir, about the other 2 roots?
So there is no sign change. So
Yes.
they'll be in left half.
Yes, they'll be in the left half plane. So very good. So no sign change. No sign change. So we have 2 roots in the left half plane. So if we summarize, total 6 roots. Out of the 6 roots, we have 2 LHP roots, 2 roots in the left half plane, and then 4 on imaginary axis. So we have to see whether do we have repetitive roots on the imaginary axis, as we have discussed in the slide 1 or the first document. If there are repeated poles on the imaginary axis, then it is unstable. Repeated means the same imaginary, the same point should not be 2. Like it should not have plus or minus j, plus or minus j. So that is repetitive. Plus or minus j is not repetitive. If the poles are on the imaginary axis, it is marginally stable. So in that marginally stable case, again, we have to check whether we have repetitive imaginary roots. So these are repetitive or non-repetitive?
Sir, non-repetitive.
Non-repetitive. Because we have one plus or minus j and another is plus or minus 2j. So there are non-repetitive imaginary non-repetitive roots on the imaginary axis and then two roots in the LHP. So the system is stable, marginally stable or unstable?
Marginally.
Marginally stable. Yes, very good. So this is one special condition where the entire row becomes 0 and then we'll consider the auxiliary polynomial, and then the auxiliary polynomial has again two conditions. The one is that it is a factor of the given polynomial, so we can find the roots of this auxiliary polynomial, which will be the roots of the given polynomial, and then the roots of this polynomial are symmetric with respect to origin. So from the auxiliary polynomial, say it has say it is instead of s square plus 4, say it is s square minus 4 equals to 0, then s will be plus or minus 2. So we'll know that one root is on the LHP, one root is on the RHP. So then we'll know one root is in the RHP. And for the remaining roots, we have to come back to the first column and then we'll get the overall roots location. And based on the overall roots location, then we can comment on the stability. So this is a like the most weirdest or like the case, like the uh, toughest case. In the other case, it is straightforward sign change. In another case, it is the sigma condition where the first element is 0, we'll consider sigma. This is an entire row becomes 0. Then you will consider the auxiliary polynomial. Imagine that even after considering the differentiation, again, if the entire row becomes 0, then again this auxiliary polynomial you have to consider and then repeat the same. So these are the different cases of the polynomials that we can encounter.
Yes.
Is that clear?
Yes, sir.
Okay. So now I think I have a few more problems. So in this problem, consider the below characteristic equation. Using the Routh Hurwitz criteria, find the range of K such that the system is stable, system is marginally stable, system is unstable. So how do you think we can proceed?
Sir, we will prepare the table,
Okay.
Routh's table.
Okay.
And if K first conditions we have to see criteria. If K is positive, then only we will proceed.
Yes.
If it is negative, means, although all the coefficients are present, but to have the same sign, K has to be positive.
Yes, very good. So the necessary condition will not be met, as you said. So first thing, in order to be stable, so if we start with the first one, first initial condition that it has to satisfy is K greater than 0. Then we'll go to the Routh table, right?
Yes, sir.
Okay. So let us draw the Routh table. So it is s to the power 4, s to the power 3, s to the power 2, s to the power 1, and s to the power 0. So what will be the first row?
1, 3, K.
1, 3, K. And the second row?
2, 3, 0.
You are making a mistake. 2?
Sorry, 2, 2, sir. 2, 2.
2, 2, 0. Right? Yeah.
Yes, sir.
So now if we calculate the s square, what will be the first value? It is product of this minus this by 2.
Yes, sir. 6 minus 2, 4 by 2. 2, sir.
2. Okay. Very good. And the next element?
K.
Okay. Very good. So now I think you have developed the speed you are telling much faster. Now, if we do the same, 2 into 2 minus 2 into K by 2. So this element?
2, 2, 2K by 2. 2 minus, sir, K.
2 minus K,
2
right?
minus K. Yes, sir.
And the last element?
0, sir.
0. S to the power 0, this element?
2 minus K into K. Sorry, K, sir. K.
K, directly K, right? Because
K.
this will directly come here. So it is K. So this is basically directly coming over here. So now if you see whatever we have discussed in this necessary condition, that same necessary condition will be also coming here, because Routh Hurwitz criteria should say that it will be stable when K is greater than 0, right? That is also coming from this point. But it is not mandatory for us to do Routh Hurwitz criterion if the necessary condition is not met. So that is just to avoid Routh Hurwitz criterion in at least some of the cases where we need not even go there and say, okay, now we have to do. So in this case, it will be directly, say if K is negative, we can directly say that it has roots in the RHP unstable. But if they ask how many, then we have to do the Routh Hurwitz. So what are the conditions for stability that we'll get from this?
Sir, first is K is greater than, all signs should be positive. K is greater than 0
Okay.
and K is less than 2. Between 0 and 2. K is between 0 and
Yes,
minus
so
2.
these are the two conditions. So K is less than 2 and greater than 0. And again, both these conditions are and, like 2 minus K should be greater than 0 and K is greater than 0. So if there is any problem, I mean, in any question, say you got two non-possible conditions. Say you got in one case K should be greater than 3 and in another case K is less than 1. So there is no K where it satisfies both. So one of the element will be negative. So in this case, such K doesn't exist, so that the system is stable. So that is also one possibility. It is not always that we'll find a K. In this case, we got 0 less than K less than 2. So in this region, the system is stable.
Yes, sir.
Okay. So first case, the system is stable when 0 is less than K less than 2. So instead of going marginally stable, can you tell me for unstable case?
Unstable, there will be sign change.
Yes.
Sign change. So this 2 minus K is less than 0, sir.
Okay.
And
Very
that
good.
means 2
K is greater than 2.
greater than 2, sir. And K and K we have considered K greater than 0.
Yes.
Overall K greater than 2, sir.
Overall K greater than 2. Or you can consider K greater than 2 and K less than 0. So this is one case that you have considered, right? So basically what I can consider is there are two conditions. So I can consider this to be negative, this to be positive, or this to be positive, and this is negative. So
Okay,
this
yes,
I'm
sir.
considering case 1, this is case 2. So in any case, the system is unstable. So in the case of case 1, so to avoid confusion, let us name it same. So in the case 1, I have 2 minus K is greater than 0, which means K is less than 2, and then K is less than 0. So K is less than 0. So in this case, what is the K value?
K less than 0.
K less than
K
0.
less than 0, sir.
And now this is case 1. Now let us come back to case 2. So in the case 2, 2 minus K is negative,
Yes, sir.
and then K is positive. So the first one will say K is greater than 2, and then second one is saying K is greater than 0. So what is the K
K
greater than
greater
2?
than 0.
Very
Yes,
good.
sir.
So these are the two conditions. In any of the conditions, system is unstable. Now I have to combine these two. So if I am combining these two, so if K is less than 0 or K is greater than 2, in both of these cases, system is unstable. So
Yes, sir.
from this also we can say, because in between 0 and 2 it is stable. So anywhere outside 0 to 2 it is unstable, which is K less than 0 and K greater than 2. So now can you comment on marginally stable?
Between the okay.
Yes, so K equals to 0 or K equals to 2.
Yes, sir.
So that you can put K equals to 0 or K equals to 2, and then we will see that one element will become 0, and then if you calculate the roots, say k equals to 0 is easy. Say if you put k equals to 0, then I will have s to the power 4, 2s cube plus 3s square
Sir.
plus 2s, right? Now I can take s common.
Yes, sir.
So one pole is at the origin, which is on the imaginary axis, so it is marginally stable.
Right, sir.
Right.
Sir.
Similarly, if you consider k equals to 2, this element will become 0. Then again, we have to replace by epsilon, and then we can do. So in that case also, we'll get 0. So it will also be marginally stable. So from here only, we can say anything that is not stable, outside that it will be unstable, and in between stable and unstable, we'll have marginally stable. So marginally stable is k equals to 0 and k equals to 2. So is this question clear?
Yes, sir.
Yeah, so this is one different way of asking. Basically, we are doing the Routh Hurwitz criterion only, but we are posing the question in a different way. What is the value of this so that the system is stable or unstable? So now, say I have given an system where I can vary one parameter. So in that system, I have the flexibility to vary a parameter, but I don't know what value of that parameter I have to select. So my overall objective is to make the system stable. So using that parameter as a variable, I can calculate the characteristic equation. And from the characteristic equation, I can get the range within which the system is stable. So say 0 to 2, the system is stable. Now I can't risk by taking k close to 0 or 2. So I'll take more conservative close to 1 at the center. So the system is stable even if there is slightly any variation. So in this way, we can judge the stability of the system. Again, this is the concept that will extend to root locus that I'll discuss on Monday, where I'm changing a gain k. So I'm changing gain from k equals to 0 to k equals to 10. How will the poles of the characteristic equation will change? Because in this case, it is going from stable to marginally stable to unstable. So if I see the poles, how they are varying, that will give me the border condition of the k below which I have to operate, right? So that is called root locus. Root locus is nothing but how the poles are moving with respect to a certain parameter that is varying. Again, this I'll discuss on Monday in detail, but I'm just giving some glimpse.
Sir,
Is
can
this
I ask?
concept clear? Yeah,
Yes,
please
sir.
ask.
Sir, this in this polynomial
Yes,
characteristic equation,
yes,
if
yes.
two consecutive coefficients are same, so then we will land into this auxiliary equation concept, right?
No, entire row is 0.
Just by seeing the polynomial, we can't actually say. I thought if two consecutive coefficients are same,
Okay,
because
you
that
meant
will
to say.
land into zero, land into zero in for. Okay, sorry, whole row has to be zero. Sorry,
Yeah.
sir.
Yeah, no, it's okay, it's okay. So if two consecutive coefficients are like same, it may not always necessarily mean that there will be a zero. Sometimes it may, sometimes it may not. I don't think I have considered any two consecutive same whole number. Like in this expression also, if 6 and 6 are there, doesn't mean we are subtracting 6 minus 6, because 6 is multiplying with 11 and then this is multiplying with 1. So it doesn't, we cannot say anything from the coefficients. We have to write the table. If you see here, like until the fourth row, nothing has become 0. So we can't even say, looking at this number, we can't say whether the roots are on the auxiliary axis. But if you see the roots, they're very simple: plus or minus j, plus or minus 2j. So after this session, during your leisure time, you can substitute and see that it will be on the imaginary axis. Only for 1 and minus 1 we can say. So if 1 is a solution, then summation of the coefficients will be 0. If minus 1 is a solution, then odd number coefficients will be equal to even number coefficients. Again, that will come by substituting it. But other than that, it is like not so easy to say anything from the polynomial.
Yes, sir.
Okay, so compared to the previous question, here k is on the coefficient side. So now k is on the some other term, not the coefficient, like the not s to the power 0, it is on some other element, but the process remains same. So what will be the stability condition? First necessary condition, as you mentioned in the previous question.
P plus K has to be positive, sir.
K plus 3 has to be positive. So K is greater than minus 3. Okay. So now let us start the Routh table. So s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. So what will be the first row elements?
1, 3 plus K.
Oh, K plus 3 and item.
And 1.
Okay. Second row?
2, 2, 0.
0. Okay. So now let us start with this. 2 into K plus 3 minus 2 by 2.
3 plus K minus 2 by 3, 2. 1, K plus 2, sir.
K plus 2. Very good. So this will be K plus 2. And then the next element?
1, sir.
1. Very good. So basically the 1 directly will come here. So and this will be 0. Now coming to
Okay.
s to the power 1 coefficient. So we'll have K
1.
plus 2 into 2 minus 2 by K plus 2.
Mhm. Okay.
How much it will be?
So, sir, 1 minute, sir.
Okay, okay, okay. Yeah. Take your time. No, I think I'm rushing you, but take your time. Slowly you can.
I, okay. The 2,
2.
2 minus
Only 2. Okay,
1
let
minute.
us let us calculate. It will be a little bit different. So
2,
K plus 2 into 2 minus 2 into 1
K
by
plus 2
K
by
plus 2.
K plus 1, sir.
2
K plus
into
1.
Yeah, so 2 into K plus 1 by K plus 2, right? So 2K plus 4 minus 2 by K plus 2. So I'll get 2K plus 2. So 2 into K plus 1 by K plus 2. So I got 2 into K plus 1 by K plus 2. And then this element will be 0, right? Next element, because right, because
0.
yeah, this into this minus this into this.
0.
Now the last element will be product of this minus product of this, or you can say that 1 will come down. So it is how much it will be?
1, sir.
1. So
Okay.
now my stability will be dependent on this first column. So what will be the condition for stability?
K plus 2 positive and this 2K plus 1 by K plus 2 positive.
Yes. So first
K plus
condition is K plus 2 greater than 0, which means I will get K is greater than minus 2. The second condition 2 I can remove. So K plus 1 by K plus 2 is greater than 0. And then if I combine these two, right? Say if I combine these two, I will get say K plus 2 is positive. So the numerator also has to be positive, right? So K
Yes,
plus 1 should be greater than 0, which means K is greater than minus 1,
right,
right?
sir.
So then only I'll get uh, the condition. So I have K greater than minus 1. This is the condition for stability.
Yes, sir.
So this is the stability. Okay, so now for unstable, we can do something similar. As I have mentioned, two cases you can consider. One is K plus 2 positive and K plus 1 negative. One is K plus 2 negative and K plus 1 positive, and see what are the possible conditions. Let us do the same. Say first I'll consider this to be positive, this to be negative. And again, we have to see whether both the conditions are possible or not. These are the possible cases I'm considering. Whether such K exists or not, that is another question. So this is case 1, case 2. So this is our first part to check the stability. Now let us check the unstable part. Unstable part, if I'm considering the first case, then it says K plus 2 is positive, which means K is greater than minus 2. And then K plus 1 by K plus 2 is negative, which means K plus 1 is negative, which means K is less than minus 1. Right?
Yes, sir.
So we are getting minus 2 less than K less than minus 1. In this region, it is unstable, right? For the case 1.
Yes, sir.
Now for case 2, it will be opposite. So let us consider case 2. So for case 2, K plus 2 is negative. So for case 2, K plus 2 is negative, and then K plus 1 by K plus 2 is positive. So if you see, K is less than minus 2. First case will say K is less than minus 2, and second case will say K plus 1 is greater than K plus 1 also less than 0, right?
Yes, sir.
Because K plus 2 is negative, K plus 1 also should be negative. Then this will say K is less than minus 1, and then K is less than minus 2. So what does this say?
Less than minus 2.
Less than minus 2. So if K is also less than minus 2, then still the system is unstable. So now combining both case 1 and 2, what can I say?
K less than minus 2. Not possible, sir.
No,
Combining.
because either this or that. So we are basically combining that. In the above case also it is unstable. In the below case also it is unstable.
Yes, sir. But here it has to be between minus 2 and minus 1, and here less than. So only at 2, only at.
No, combining in the sense not intersection, union. Okay. I think I might have confused you. So in this column, either case 1 is possible or case 2 is possible, right? So if this is positive, this is negative, this is negative, this is positive. So I have to select that entire range of K where any of this possibility can happen. So now I have considered case 1, and then I got if K is lying between minus 2 to minus 1, it is unstable. And then for case 2, I got if K is less than minus 2, it is unstable. So if I consider, I think now if I consider like a line here, so minus 1 and minus 2 are all points, right? So minus 2, we have minus 2 over here, and then minus 1 over here, and then we got anything above minus 1, it is stable. So I'll consider green color. So anything in this region is stable. And then I got anything in minus 2 to minus 1, it is unstable. So this is unstable. I also got if K is less than minus 2, again it will be unstable. Right? Got it? Or is it?
Sorry, sir. Yes, sir.
So now I have to combine the entire region. So this entire region is unstable region.
Right.
So now I will get combining these two. K is less than minus 1, then it is unstable. So if K is less than minus 1, then it is unstable. So for marginally stable, we have K equal to minus 1. So basically, if K is less than minus 2, then the second case will happen, which means this is negative and this will become positive.
Yes,
But
sir.
K is lying between minus 2 and minus 1, then this will become positive, this will become negative. So in this case, there are two roots on the RHP side because there are two sign changes. Again, in this also there are two sign changes. There are two roots on the RHP. But either this will happen or this will happen. So in one case, the range of the k is less than -2. In the other case, it is from -2 to -1. But if I take in any of this entire region, the system will be unstable. Only the negative will be happening in s square in one time, s to the power 1 in another time, but both will lead to instability.
Sir.
Is that clear?
Yes, sir.
Okay. So I think marginally stable. Then I have considered another such problem, which is transfer function is given, and then I think I have not given the block diagram. So let me draw the block diagram. Pace is okay, right? It is not fast, right? Or should I slow it down?
Right now, okay, sir.
Okay. This is the so this is u of s. This is y of s. Again, here I have not directly given the characteristic equation. I have given a block diagram, and from the block diagram, I am asking to calculate. So, like the user or the student has to calculate the characteristic equation. So this is GC of s, and then this is G of s. So, what will be the characteristic equation?
S into S minus 1, S plus 2.
Okay, let us
We have to
calculate the
make
closed loop.
yes, sir.
Sorry,
Closed loop.
closed loop
We
will
have to make
calculate.
a closed. Yes, sir.
So y of s by u of s, which is GC into G by 1 plus GC GH, right?
Yes, sir.
So if I do that, I will get K by S into S minus 1 into S plus 2 by 1 plus K by S into S minus 1 into S plus 2. So this will be equal to K by S into S minus 1 into S plus 2 plus K. So this is my region of interest, right?
Yes, sir.
So this denominator is what is my characteristic equation. So
Yes, sir.
the question is, let us consider the characteristic equation, which is S into S minus 1 into S plus 2 plus K.
Okay.
So this is S into S square minus, plus S minus 2 plus K. So the equation that I will be getting is S cube plus S square minus 2S plus K. So this is the characteristic equation that was given in the previous questions, but in this question I have gone slightly backward and two steps we have to calculate, which are the characteristic equation from the closed loop transfer function. So now the question is, find the value of k or the range of k for which the system is stable. So how do you think we can proceed? Or is there any catch?
Sir, it is criteria is not meeting here.
Yes.
-2. One of the coefficient is negative.
Yes.
Yes, sir.
Yeah.
So we need not to proceed to.
Yes, yes, very good, very good. So this is such a type of question where for any value of k, we will never be able to stabilize the system. So very good. So the k is not part of this -2. Had it been k -2 and say this is some positive number, we could have done something. But in this case, no matter the value of k, the necessary condition is not met. So no such value of k exists. Very good. So no such value of k exists. So there is no such value of k. Again, I would like to give some more insight to this problem. So whether g of s is stable, just g of s,
No, sir.
it is not stable, right? It's an
Yes,
unstable
sir.
system.
Yes, sir.
And usually we call this as plant. So g of s is plant, and then this h of s is feedback,
Mhm.
and then this gc of s is called controller. So basically the again we'll learn this in the upcoming weeks. I'm just giving an insight because this problem is interesting. Basically here what we are trying to do is I am finding, does any controller exist for which the overall system can be stabilized or not? So for this given system, if I'm considering a constant gain k as a controller, I can never stabilize it, right?
Right. Yes, sir.
Yes, we cannot stabilize it. But is there
Mm.
any way to stabilize, or what we have to do? That again brings back to this point that k is a coefficient with coefficient of s to the power 0. But the issue is lying in the coefficient of s to the power 1, right?
Yes, sir.
So as long as we consider only a coefficient k, s to the power 0, we can't stabilize the system. But is there any way, if we consider instead of k some other polynomial, that
Okay,
will
okay.
bring back
Uh,
to the next problem. So I have considered again the same problem, and that thing is same. So it is just if you see 1 by s minus 1 s plus 2 k and 1. Now here I have considered, instead of k I have considered ks. So this is what I have considered to check whether the system can be stabilized at all if I'm varying gc, because my objective is to design a controller to stabilize the system. So let us see. So let us take this expression and then let us go back there. So y of s by u of s is gcg by 1 plus gc into h. So let us calculate and see whether we can do anything or not. So we'll get k into s by s into s minus 1 s plus 2 by 1 plus k into s by s into s minus 1 into s plus 2. So here I'll get ks by s into s minus 1 into s plus 2 plus ks. So again, this is my area of interest. So this is the polynomial characteristic equation that I'll be considering. So let us consider it. Characteristic equation. So this is s into s minus 1 into s plus 2 plus ks. So we'll have s into s square plus s minus 2 plus ks. So if I consider, I will get s cube plus s square plus k minus 2 into s. This is the expression that I got, characteristic equation. So from this, can we say anything?
Sir,
Or
again, it is not meeting because s to the power 0 coefficient is not available.
s to the power 0 is not available. But again, maybe I should have told at that point. So if s to the power 0 is not available, then you can take s as common, right? So now let us say this I am slightly modifying. I will take s common, okay? So I'll take s common, then I'll get s square plus s plus k minus 2, right? So now can we say anything, or
One is marginally stable, if we are seeing, and then k minus 2 has to be positive for.
yes. Yes, very good. So when the coefficient is missing, like the s to the power 0, one root is always at the origin. So it is marginally stable. So that's why the Routh Hurwitz criteria, basically it is to check for the stability, right? So that's why this is necessary. All the coefficient should be there. If any of the coefficient is missing, it means the coefficient is on the imaginary axis or on the right half side. So it will be on the imaginary axis if s to the power 0 is missing. But had it been any other coefficient, then it is on the right half plane side. So that is the more specific one, if I am more clear. So now let us write the Routh Hurwitz of this. So we can get s square and then s and then s to the power 0. So s square is 1 and k minus 2. This is 1 and again this is 0. So we'll get k minus 2. So which is what again you said. So k is greater than 2. So if k is greater than 2, then what it will be? The system stable or unstable or marginally stable?
K greater than 2 is stable, sir. K
What?
greater than 2.
This
The-
s square plus s plus k minus 2 is stable, but including s?
That is marginally, making it marginally stable.
Marginally stable. So overall system is marginally stable. So if you see, the objective of the previous question was to design a controller or find if there any controller exists to stabilize the system. And if we put just coefficient, we saw that no such value of k exists. But now if I put k into s, then I got, because the coefficient is missing, because there is no s to the power 0, one root is always at the 0. And in that case also, k has to be greater than 2 so that it will be marginally stable. So now if I go one step further, if I consider k1 s plus k2, then I'll get k1 minus 2 plus again k1, right?
Yes, sir.
So then all the terms are there. Then in that case, I can find the range of k1 and k2 and see whether it can be stabilized. So the system, unstable system can be stabilized, but what value of controller or what transfer function of controller I have to choose, that will check whether the system is stable or not for that controller. And the overall objective of this control system or the entire course is to design a controller so that the system is stable and it meets the consumer requirement. So that is the overall objective.
Sir.
Clear, right? It's an interesting
Yes, sir.
question, right?
Yes, sir.
Yeah. So just I'm giving the knowledge so that you can correlate. Again, this controller will come in the maybe 2-3 weeks later, but you will have that idea in the mind, and when we discuss, like you can correlate with this. So that's why I have considered that problem in two parts. But I have not considered K1S plus K2 because two unknowns will make it complicated. The objective is to give the idea, but not complicated, because that difficult is not there in the week 4 assignment. So I have stopped at K1S, I mean K into S. So till this point, it is clear, right?
Yes, sir.
Okay. So now coming to another important topic, sensitivity, and we'll solve 1 or 2 problems on this and we'll end this session. So sensitivity is related to any parameter in the given system. Say we have unity feedback system or non-unity feedback also. So G of S and then H of S. So how sensitive is the system? If there is any parameter, say G of S has some parameter or H of S has some parameter, how sensitive is the overall system with respect to that parameter? So this is my Y of S. This is my U of S. This is plus minus. Say H of S or G of S has a parameter. Say parameter is A. So one of this has a parameter A. So now sensitivity is defined as sensitivity of the T. Again, T is called the closed loop transfer function, which will be G by 1 plus G, right? G by 1 plus G. So T is always considered as G by 1 plus G. So the sensitivity of the closed loop transfer function T with respect to that parameter that is varying A is defined as change in the closed loop transfer function, ratio of change in the closed loop transfer function with ratio of change in the parameter A. So now we will see by solving a problem. This is a definition. So in the given closed loop system, there is a parameter that is varying. So sensitivity is nothing but how much sensitive is the overall closed loop system with respect to the parameter. So now that sensitivity is defined as dou T by T, which where T is the closed loop transfer function and dou A by A is the parameter. So this is the definition. Using this definition, now we have to calculate the sensitivity transfer function and see how much sensitive is the closed loop transfer function with respect to that parameter. Now, if we check the closed loop poles by varying that parameter, that is called root locus. That we'll discuss on Monday. Is this clear or should I repeat it once more?
Clear, sir.
Clear. Right? So if it is clear, we'll quickly solve a couple of problems on this. So this is the concept. Coming to the problem. So consider a unity feedback system, which means h of s is 1. So I have given h of s is 1. And a is the varying parameter. So let us calculate first t. So what will be t in this problem?
Into the T will be the 1 upon
Okay.
S square plus AS plus 1.
Yes, very good. 1 upon s square plus as plus 1. Very good. So now let us go back to the definition of sensitivity and then we'll just use the sensitivity formula. So this is just a definition and giving some insight of how, like, when we are designing, say, um, some control closed loop system and there is something varying. So we have to see whether that varying parameter will cause any instability in the system. We have considered aeroplane, right? Aeroplane we have seen in the earlier weeks. The aeroplane mass is dependent on time because the time at which it is taking off and the time at which it is landing, the mass is different. So now it is very important to see the stability of the aeroplane with respect to the mass and how much sensitive is the overall closed loop with respect to mass, because that is very important because mass is varying and there are certain other things that will also vary, like temperature will vary when we go at certain altitude, and then pressure will vary, humidity will vary. So these are some parameters that will vary in the process and we have to see how much sensitive is the closed loop. Say if the closed loop is insensitive or it rejects all the this variation in the parameters, then we call it robust system, which means it is robust to any parameter variation. So that is what any control engineer objective is, to design one robust control system. So here g of s is 1 by s into s plus a. So t of s is 1 by s square plus as plus 1. So now the sensitivity expression is nothing but, let me use a different color. I am using the same color. So sensitivity is dou t by t by dou a by a. So if I change it, I'll get dou t by dou a, which is partial differentiation of t with respect to a into a by t. So if you solve what is differentiation of t with respect to a, so here a is again small a, right?
Yes, sir.
Parameter is small a, dou t by dou a into a by t. Yeah, so yes. So what is the differentiation of t with respect to a? So I'll give some formula. So if I have t is equals to 1 by function of a, then dou t by dou a will be minus 1 by f of a whole square into dou of f of a by dou a. So this is the formula that we have learned in the differentiation. So now can you tell?
Yes, sir. 1 minus 1 upon a square plus a square plus 1.
So what will be the minus 1 by f of a whole square?
My, minus 1 upon a square, 2a square plus 1 whole square. So,
Okay. I think so. Here f of a is what? F of a is think
uh,
so f of a is 1 by s square plus as plus 1, right?
yes, sir.
So now dou t by dou a is minus 1 by f of a whole square, which means minus 1 by s square plus as plus 1 whole square. Now into differentiation of f of a with respect to a, not with respect to s, because we are not differentiating with respect to s. So if I am differentiating s square plus as plus 1 with respect to a, then s is assumed to be constant. So it will be dou by dou a of s square plus as plus 1, right? So it will be s, right? Because we are differentiating only with respect to a. So s square will become 0 and 1 also will become 0.
Yes, sir.
So it is only s, right?
Only yes.
Only s. So this is s, and then a by t is what? T is 1 by s square plus as plus 1. So now the sensitivity of the overall closed loop system with respect to this parameter is nothing but minus as by s square plus as plus 1, because this will get cancelled with the square, one of them. So this is the overall sensitivity. Now, if you see, this sensitivity is a function of S, right? So depending upon the frequency, the sensitivity can vary. So now you have to see at what frequency it is more sensitive, at what frequency it is less sensitive, and then we can study the sensitivity also. And again, it is dependent on the parameter A. Say if A is big, how sensitive it is. If A is small, how sensitive it is. So in this way, we can study how much sensitive is the closed loop system with respect to that parameter. Is the concept clear?
Yes, sir.
Okay. So now let me solve one more problem. This is the final problem. So here a is in the denominator. Now here a is in the numerator. Again, feedback system. So now I'll like now you can do it by yourself, because in the last problem you have made small mistake. So now you'll get another chance to correct yourself. So t is nothing but g by 1 plus g, right?
Yes.
Yeah, so now if I calculate, maybe you can calculate, I'll give you some time, you can calculate and tell me what is T.
Sir. The 4a plus 1 upon s plus 4a plus 6.
S plus 4a plus 6. Yes, very good. So this is by T. Now sensitivity is defined as dou T by T by dou A by A. So what I'll be doing is I'll be differentiating dou T with respect to A into A by T. So if I have again T is equals to F1 of A by F2 of A. So I will get you know the formula, right? Dou T by dou A is F2 into F1 dash minus F1 into F2 dash by F2 square. Like differentiation of U by V is V du minus U dV by V square, right? So that is what I have done here. You are aware of this formula, right? Here it is a function of A, so it feels little bit different compared to what we have differentiated with respect to S. So that's why here it feels little bit off.
Yeah, right, sir. The del T by del A.
Del T by del A is, should I also calculate, or you have calculated this, right?
Calculated.
Okay.
Please verify. Del T
Okay.
by del A is equal to minus 8A plus 4S plus 20 upon 4A plus S plus 6 whole square.
Okay. Into A by T.
Yes, sir.
Okay. So let me verify. So dou T by dou A. So now if I consider dou T by dou A, it is F2, which is S plus 4A plus 6 into F1 dash with respect to A, which is 4, minus F1, which is 4A plus 1 into F2 dash, which is again 4, by S plus 4A plus 6 whole square. So it is 4S plus 16A plus 24 minus 4A minus 4 by S plus 4A plus 6 whole square. So it is minus 8A plus 4S plus 20 by S plus 4A plus 6 whole square. Yeah, I think you have told correctly. I have written it here in a wrong way. So whatever you have told is right. So this is minus 8A plus 4S plus 20. Yeah. So whatever you have said is correct. So now if you calculate sensitivity S.
A by T, sir.
Yes, A by T also I'll calculate. So if I do minus 8A plus 4S plus 20 by S plus 4A plus 6 whole square into A by, now T is what? 4A plus 1 by this term. So it is 4A plus 1 by S plus 4A plus 6. So now this will get cancelled with the square. And finally, whatever answer that we'll be getting is S sensitivity is equals to minus 8A plus 4S plus 20 into A by S plus 4A plus 6 into 4A plus 1. So this is the overall sensitivity. So depending upon the A, see if it is in the denominator, our life was simpler. The expression was also simpler. But if it has gone to the numerator, again, the situation is a little bit complicated. So now if we have second order, then it will be a little bit complicated. So depending upon the complexity of the system and the location of the A, the things can vary, and like expression can get complicated. But the like objective of this problem is to understand how to check the sensitivity of the closed loop transfer function with respect to the variable A. So I've considered one problem in the denominator, one problem in the numerator. And this is the way only we should be careful with the partial differentiation. If that is done properly, then I think it is easy only. So is this concept clear?
Yes, sir.
Okay. So if you have any doubts, you can ask, else I'll summarize this session. So that's all about today. Any doubts? Or I can summarize.
I am clear with whatever you explained, sir.
Okay. Then I'll just quickly summarize. So in week 4, we have learned about stability as well as Routh Hurwitz criteria and sensitivity. So we have started with stability. We have understood using simple pendulum example what is stable, what is marginal stable, and what is unstable system. And then we have also understood BIBO stability, which is bounded input, bounded output stability, and it is in time domain. Then we have moved to the definition that which is the impulse response should be absolutely integrable. So if we want to check the stability in time domain and if the system is LIBO stable, we have to perform this integration, and it is from 0 to infinite, and the integration should be less than infinite. And in the case of frequency domain, we have to check the pole location, and we have found out that on the imaginary S plane, if the poles are on the left side, it is stable. If they are on the right side, it is unstable. If they are on the axis, it is marginally stable. And if the repeated poles are there on the imaginary axis, that is also unstable. So the objective is to find the pole location, and for that we have learned the Routh Hurwitz criteria, and we are only bothered about the characteristic equation or the poles of the system. And the necessary condition is the polynomial should have all the coefficients and the coefficient should be positive. If the given polynomial fails to meet this necessary condition, it means it has again on the imaginary axis or on the right hand side. But if it has a negative sign, it means it is on the right hand side. Only if the s to the power 0 coefficient is missing, then it has pole at origin. Then we have seen how to calculate the Routh table. We have solved a few problems. The first problem is straightforward and second problem has one condition, which is the first element in the row. If it becomes 0, we have to replace it with epsilon greater than 0 and finish the Routh table. And we'll have to put epsilon certain value and then check if there are any sign changes. Number of sign changes equals to number of poles in the RHP. And from there, we can get whether the system is stable or unstable. Then we have solved two more problems, which are also straightforward, and there are sign changes and there are no sign changes. And then we have came across one interesting problem where the entire row becomes 0. In such case, how do we get the coefficient in that row? Then we'll use the polynomial above that equation, which is defined as auxiliary polynomial. We'll differentiate it and use those coefficients in the current row where the entire row has become 0 and finish the Routh table. And once we finish the Routh table, we should go back to the auxiliary polynomial, which is a factor of the given polynomial. So by considering the roots of this auxiliary polynomial, we'll get the roots of the original polynomial, and these roots will be symmetric. So from this, we got four such poles on the imaginary axis. And from the Routh Hurwitz, we have seen that no sign change. So the remaining two poles are in the left half plane, and these four are on the imaginary axis. Then we have solved a few more problems where we have asked the k range of k so that the system is stable or unstable. And in this problem, I have not given the characteristic equation, but I have given a closed loop system, and I have asked whether is there any k such that the system can be stabilized. And one case it is not possible. In the other case, I have given ks, and then we got marginally stable. And even for marginally stable, k has to be greater than 2 because this second order has to be satisfying the necessary and sufficient conditions of the RH criteria. Then we have learned about sensitivity. First, we have learned about the definition, and then we have quickly solved two problems where in one case I have considered a in the denominator, and in the other case I have considered a in the numerator, and we have solved this problem. So that's all about week 4. If you have any questions, you can ask. Else again, we'll meet on day after tomorrow, Monday, with root locus. Again, that will be also very interesting.
Thank you, sir.
Thank you. Yeah. One thing I would like to say that you have been very interactive, and this session was so nice, like one of my best sessions in the recent times. And you have also joined by going through the lecture site, so it helps you as well as me, so that it will motivate me to teach more and more, and also you'll also get benefited. And yeah, thank you for making
Thank
this
you,
session
sir, for
very
being
interactive.
patient with me.
Yeah, yeah. By the way, where are you from? Like, are you BTech student or MTech student?
I am not a student, I am working.
Oh, okay, okay.
So as a interest, just to continue with the studies, I have taken this course.
Okay, okay, okay. So like you are currently working and then you are interested in control, so you have taken this
Yes,
course.
yes,
Okay,
just to
okay.
enable with the technologies.
Yes, 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 nice. And controls is actually very much needed in most of the like any applications, irrespective of that, control is mandatory, and this knowledge is very crucial. And I hope I
Thank
will
you.
be able to help you, and you'll get benefited from this course.
So nice of you. I really enjoyed the session. Thank you,
Yeah,
sir.
yeah, yeah. Okay, see you again on Monday, and I wish you all the best for assignment 4. Okay, then
Thank
have
you,
a
sir.
nice day. Good night.
Same to you, sir.